Hi, in this set of lectures we're talking about prediction. And here's the idea. We want to think of individual people make prediction based on models. Those models could be based on categories or linear models or Markov models. Any of the models you've learned in this class you could use to make some sort of prediction. And what we want to talk about is where collective wisdom can come from. So if we have a whole bunch of people using a whole bunch of different models, how does that enable the crowd of models to do better at making sense of the world and making an accurate prediction? Now, the essence of our argument is going to be something called the diversity prediction theorem. And the diversity prediction theorem is going to relate the wisdom of the crowd to the wisdom of the individuals. So, in other words, the accuracy of the crowd in relationship to the accuracy of the individuals. Now, one logic that should come to you right away is that if I have more accurate individuals, I should also get a more accurate crowd. But a logic that might not come to you right away is that if I have a more diverse crowd, I should also get more accuracy. So we can think of things like the crowd's accuracy is going to depend on the individual accuracy plus the diversity. Now the question is, how much do these things matter? How much does it depend on individual accuracy and how much does it depend on diversity? That's what we want to use a model to figure out. So let's first do an example just to get some bearings in terms of what it means for a crowd to make a mistake versus an individual to make a mistake and what diversity is. So we're going to do an extremely simple example. We're going to have three people, Amy, Belle, and Carlos. And let's suppose that they're picking the number of people that come to our diner on a particular day for lunch. And so Amy predicts it's going to be 10, Belle predicts it's going to be 16, and Carlos predicts it's going to be 25. Now if I add these up, I'm going to get 51, and divide by 3, I'm going to get an average value of 17. So the crowd predicts 17. Now let's suppose the actual value is 18. Now, again, I've set this up so the crowd is pretty accurate. That's not going to matter, but this is just for the purpose of the example. I'm going to make it so the crowd actually does pretty well. We just want to work through the logic. So the first thing I'm going to do is I want to figure out how accurate are these people. Well, what I can do is I can compute the error of each person. So remember the true value was 18. That's the number that showed up. And I can ask what's the error of each individual. And remember we computed errors by looking at variation, squared error. So Amy predicted 10. The truth was 18, so her squared error is 64. Belle predicted 16, the true value is 18, so her squared error is 4. Carlos predicts 25, the true value is 18, so his squared error is 49. And if we add all those up, I get 117. And if I divide by 3 to get the average error, it's 39. So on average, these people are off by 39. Some people, Belle, are really accurate. She's only off by 4. Other people, Amy, is off by quite a bit. She's off by, her error is 64. But the average is 39. So this sort of gives us a sense of how accurate the individuals are. The individuals are off by 64, 4, and 49 for an average of 39. Now we can ask how accurate was the crowd. Remember, the crowd predicted 17 because that was the average prediction of the three people. The actual value was 18, so we get the crowd is only off by 1. So the crowd here is, if you notice, better than anybody in it. So we get, quote unquote, the wisdom of crowds. Well, let's try and think about why that makes sense. And to do that, we're going to look at diversity. So diversity, I'm just going to think of as the variation in the predictions. So how do we do the variation in the predictions? We look at each person's prediction and its distance from the mean prediction, not from the true value, from the mean prediction. So the mean prediction was 17. So Amy's contribution to the sort of total variation of the prediction is just 10 minus 17 squared, which is 49. Belle's is 16, this should be a 17, minus 17 squared, which is 1. And Carlos's is 25 minus 17 squared, which is going to be 64. Now if I add all these up, I get 114, and if I divide by 3, I get 38. So the diversity of these predictions is 38. Well, notice this. The crowd's error was 1. The average error was 39, and the diversity was 38. So I look at that, I get 1 equals 39 minus 38. The crowd's error, in this case, equals the average error minus the diversity. But I just set this up. Well, it turns out that's always true. This is what the diversity prediction theorem says, that the crowd's error equals the average error minus the diversity. Now this isn't some feel-good statement. This is a mathematical fact. This is an identity. So no assumptions have to be made here. There's no opposite proverb. This is just true. If I have a set of predictions, it will always be the case that the error of the crowd, so the average error is squared error, the average prediction squared error, is going to equal the average squared error of the people in that crowd minus the diversity of their predictions. Now, the way to write that formally is like this. Now, this looks pretty scary, but let's just walk through it. So let's let C be the crowd's prediction, theta be the truth. So theta is equal to the true value. And so this is just saying this is the crowd squared error. So it's the distance from the crowd to the truth. Let's let SI here equal individual I's prediction. So individual I's prediction. And so we're going to get, this is I's prediction minus the truth squared. And then we sum that up over all the individuals, and we divide by the number of individuals. So that's just going to be the average error. So crowd's error equals average error minus, now we take each person's prediction minus the crowd's prediction, which is C. Remember, because C is the crowd. So this just tells us how far people are from the crowd on average. We sum those up and divide by n. So we get the crowd's error equals the average error minus diversity. Now, if you take this equation and expand all the terms and cancel everything out, you'll see that it's an identity. It's a mathematical identity. So it's always true. Crowd's error equals average error minus diversity. Let me give a famous example to sort of drive this home. So in a book called The Wisdom of Crowds by Jim Surowiecki, he talks about the 1906 West of England Fat Stock and Poultry Exhibition. At this exhibition, 787 people guessed the weight of a steer. Their average guess was, I think, 1,197 pounds. The actual weight of the steer was 198 pounds, so they're only off by a pound. So you can look at that and say, oh my gosh, that's amazing. That's the wisdom of crowds. But let's think about it. What's going on? We've got a bunch of predictions. There's a true value. There's an average value. Our theorem, this thing, this diversity prediction theorem, must hold. And in fact, if you take Galton's data and you plug it all in, here's what you get. The crowd's error is actually a little bit less than a pound. It's 0.6. The average error is 29.56. Now, wait, that seems crazy because remember, this steer only weighs 1,100 pounds. So if this thing weighs 1,100 pounds, how could they be off by 29.56? Well, remember, these are squared errors. So if I square 50, I get 2,500. And if I square 60, I get 3,600. So this is probably 55, 56 squared, something like that. Well, that makes sense because people could probably guess the weight of a steer within about 55, 56 pounds. Well, why is that? Well, think about it. A steer is 5 times the size of a person. You can guess the weight of a person within about 10 pounds. So you can probably guess the weight of a steer to within about 50 pounds. So what you've got is you get some sort of, people who are reasonably good at guessing the weight of steers. They're not geniuses, but they're also not crazy. They're not guessing 50,000 pounds. So these are reasonably knowledgeable people who, for whatever reason, are, making these errors of about 55, 56 pounds. Now, what's interesting is that their diversity is 29.55. So what you get is the crowd is wise because they're moderately accurate, right, drop by 55, 56 pounds, and they're also diverse. And it's that accuracy plus diversity that makes the crowd do so well. Now, if you think about this book, The Wisdom of Crowds, where Surowiecki gives a bunch of examples where that's the case, let's think about it in the context of our theorem. So we've got crowd error equals average error minus diversity. Now, in this book, Surowiecki says, here's what matters. Diversity matters a lot. Well, why does diversity matter a lot if we're looking at the wisdom of crowds? Let's see. There's actually, the math will tell us why. If you make it into the book, The Wisdom of Crowds, what has to be true? This has to be small. The collective error has to be small. Because if the collective error isn't small, it doesn't make the book. It's not the wisdom of crowds. It's the madness of crowds. So for the wisdom of crowds to exist, this has to be small. Collective error has to be small. Let's think what else has to be true. The average error has to be fairly large. Why does it have to be fairly large? If the average error is small, that means that it was an easy thing to predict. Everybody can pretty much get it right. So if it's interesting enough to make a book called The Wisdom of Crowds, where the crowd is smart and the people aren't, if the people are not smart, that means the average error has to be large. Well, if you got something small equals something large minus something else, this other thing has to be large, which means diversity has to be large. So when Surowiecki walks through all these examples and he looks at what's going on, he says, look, there's a lot of diversity, and diversity seems to be a key component in the wisdom of crowds. You want to encourage people to think about the world in different ways if you want to get the wisdom of crowds. And our model explains why that's the case, because collective error equals average error minus diversity. If people aren't that smart, average error is going to be big. If you want the crowd to be smart, the only way to get it is by having that crowd be diverse. So if we look at the first example of Galton-Steer, where we get 0.6, 2956, and 2955, we see that's exactly the case. Small crowd error, fairly large average error, because it's not an easy thing to do, and then high diversity. And if you take examples of wisdom of crowds from all over the place, you'll see they all look like this. They look exactly like this. Small crowd error, large individual error, large diversity. The question is, how do you get that diversity? Well, you get that diversity by people using different categorizations, different linear models, maybe people using entirely different models. Maybe one person's using a Markov model and one person's using a diffusion model. Maybe one person's using a linear model, maybe one person's got a nonlinear term in their model. Maybe people have different variables. So what you get is this heterogeneity in how we see the world, and the boxes we use, and the variables we use, and the models that we construct are what give diversity to these collective predictions. And that those collective predictions then lead to accurate crowds, provided you've got reasonably accurate people who are reasonably diverse. And what we've learned is by constructing a very simple model of that predictive task, where the wisdom of crowds come from. And we've learned that individual ability and collective diversity matter equally. They're equal partners. So if someone were to say to you, well, where does the wisdom of crowds come from? You could say, well, it comes from, reasonably smart people who are diverse. And you can also ask, where does the madness of crowds come from? How could it be that a crowd could get something totally wrong? Well, that's not hard either, because crowd error equals average error minus diversity. Well, if I want this to be large, if I want large collective error, then I need large average error, because I need people to, on average, be getting things wrong, and I need diversity to be small. So the madness of crowds come from like-minded people who are all wrong. And again, the equation gives us that result. All right, thank you.